Hello everyone, welcome back to my channel. In our last video, we have given discussion regarding classification of phenols. So phenols are having very great importance in industrial chemistry. Means by starting with phenol, we will be preparing most important compounds in the field of science. Say for example, salicylic acid, salicylaldehyde, and by starting phenol as one of the starting material, we are going to prepare the most using material in current life, that is plastic. In a strictly speaking way, bakelite plastic, which will be also called as phenol formaldehyde resin. In such a way, phenols are having very great importance and they will be using as starting materials in preparing many compounds. And such compound which will be prepared by taking phenol as a starting material is salicylaldehyde. And of salicylaldehyde is having very great importance in the field of organic chemistry. Detailed mechanistic pathway for the preparation of salicylaldehyde starting from phenol was actually given by two scientists by name Reimer and Tiemann. So Reimer Tiemann reaction is having great importance in the field of organic chemistry with respect to phenols. In this session, we shall look over into the Reimer Tiemann reaction for the preparation of salicylaldehyde starting with phenol, and we shall look over the detailed mechanism for the Reimer Tiemann reaction. So according to Reimer Tiemann reaction, it is simply the formylation, because we know that the aldehyde group is also called as formyl group. So phenol will be formylated, means the aldehyde group will be created on the benzene ring of the phenol. So in that way we can say Reimer Tiemann reaction is simply the formylation of phenol. And in converting phenol into salicylaldehyde, we use the materials, that mean phenol is first reacted with CHCl3, that what we call as chloroform, and the reaction will be performed in basic medium, so that we will be using either sodium hydroxide or potassium hydroxide. These are the components that will be present in Reimer Tiemann reaction. So phenol is first reacted with chloroform and sodium hydroxide or potassium hydroxide, so as to get, by the reaction of all this, we are going to get salicylaldehyde. That is the final product in Reimer Tiemann reaction. Okay, fine. And here, if you go with the reaction of Reimer Tiemann reaction, or else if you go with equation of Reimer Tiemann reaction, phenol will be reacted with chloroform CHCl3 in presence of potassium hydroxide, we are going to get salicylaldehyde. And one doubt may comes to our mind. So at which position the aldehyde group is going to create? And answer for that is, you can notice the group which is present on the benzene ring. And here the group present is OH group, which is an electron donating group. So we know that if an electron donating group is present on the benzene ring, that will direct the incoming group, that may be an electrophile. Okay. So in a strictly speaking way, the Reimer Tiemann reaction is a very best example of electrophilic substitution reaction. The Reimer Tiemann reaction is the electrophilic substitution reaction. So in order to account for the position of the incoming electrophile, that means the position on the benzene ring to which the incoming electrophile will attack, obviously we should observe the nature of the group which is already present on the benzene ring. So we know that if the group which is present on the benzene ring is an electron donating group, then that will direct the incoming electrophile to ortho or para position. So that we used to call the electron donating groups as ortho-para directing group. And if the group present on the benzene ring is an electron withdrawing group, then that will orient the incoming electrophile towards the meta position. That's why we used to call the electron withdrawing groups which is present on the benzene ring as the meta directing group. But if you come to the case of phenol, the group which is present on the benzene ring is OH group. The hydroxy groups are electron donating group. So the incoming electrophile will be directed to ortho and para position. So that when you perform formylation of phenol with chloroform and potassium hydroxide, the formyl group means the aldehyde group may create either at ortho position or at para position. So this is ortho hydroxy benzaldehyde. This is the IUPAC name of the salicylaldehyde, and this will be para hydroxy benzaldehyde. So here I have written the IUPAC names of the material, or in a strictly speaking way, this is ortho salicylaldehyde and this is para salicylaldehyde. Okay, so these are the two products we are going to get when the phenol is subjected to formylation. But among ortho and para products that are produced in Reimer Tiemann reaction, this ortho product is the major one and this para product is minor one. The reason for this particular product to obtain as a major product is the presence of CHO group at this position will result in easier hydrogen bonding in the material. But if you come to the case of para, the formation of intramolecular hydrogen bonding is not possible in case of this product. So the ortho substituted product is the major one compared to the para substituted. But in case of substituted phenol, if the ortho positions were blocked, if any group is present at the ortho position, then the formylation will obviously occur at para position itself. In that case, the para substituted salicylaldehyde will be the major product. But when ortho positions are free, compared to the para substituted, ortho substituted compound will be the major product. And this is the simple thing about the Reimer Tiemann reaction. This is the equation what we can give for Reimer Tiemann reaction. Okay, now we shall go to the actual part of this session, that is the mechanism of Reimer Tiemann reaction. This Reimer Tiemann reaction is actually occurs in two important steps, actually three, but we shall say in a complete details manner. So here, as I said, this Reimer Tiemann reaction is an electrophilic substitution reaction. So first, the electrophile should get generated, and then that electrophile should attack the benzene ring, preferably at ortho position, so as to produce the formyl group at ortho position to get the salicylaldehyde as major product. So here I have written only So here I have written only the ortho substituted product, which is considered which is the major product. So now we shall go with the mechanism of Reimer Tiemann reaction. So in step 1 of Reimer Tiemann reaction, we are supposed to generate the electrophile. So we know that the electrophiles are the electron deficient species and they have the tendency towards the lone pair of electrons or the pi electrons which are present in the benzene ring. So if you go with the generation of electrophile, first the chloroform will comes into picture with the reaction of the base that what we have taken, that is potassium hydroxide. So here the base material, the aqueous solution of KOH will be taken. So the OH minus content which is produced from the potassium hydroxide will first attack the hydrogen atom which is present in the chloroform, so that this OH minus will pick the hydrogen. So these two electrons, one bond is equals to two electrons, so this bond will shift on to carbon atom, creating a lone pair on the carbon atom. So here we observe the elimination of one unit of water molecule which is formed by combination of OH minus with H plus. So we will be getting C, Cl, Cl and Cl with one lone pair of electron. But we have taken only OH minus from KOH, but still we are having K plus over here, and that K plus will now comes into picture. So these two electrons, the bond pair of electrons will go to the K plus, and that results in the elimination of KCl. So finally we will be getting this thing, that is the required electrophile. So you can notice over here carbon is in the divalent form with one lone pair of electron on it. We know that if the carbon atom is in the divalent state with one lone pair of electron on the carbon atom, we call that as carbene, right? And here we are having two chlorine atoms. So the electrophile which is required for us in this particular reaction is dichlorocarbene, which is the required electrophile in this reaction. So this is the first step of Reimer Tiemann reaction, that is generation of electrophile. Okay, we said in step 1 there occurs generation of the required electrophile, that is dichlorocarbene, and in the second step there occurs attack of the electrophile on the benzene ring of phenol. So that is attack of electrophile on the benzene ring, and the further changes will result in the final production of the salicylaldehyde, that is the creation of formyl group on the benzene ring. So here we have taken the phenol. So now again the base will comes into picture, that is OH minus. So this OH minus will attract the H of the phenol, and this bond pair of electron will shift on to the oxygen, so that there occurs elimination of H2O. So that again results in the formation of O minus over here, that is phenol is first converts into phenoxide ion, and to this phenoxide ion the dichlorocarbene will attack. So this is electron deficient species. So the lone pair of electrons are present on the carbon atom. Since it is an electron deficient species, because the valency is not satisfied and the octet is not completed, so it is electron deficient species, so it need of electrons. So this pi electrons which are present over here will attack the electron deficient carbon atom, and to balance the valency of the carbon atom, this negative charge will shift and distribute between the oxygen and carbon atom and creates the double bond. So in this way. So here due to shift of the electrons there occurs a double bond between carbon and oxygen, and here the hydrogen and carbon with two chlorine atoms and with a lone pair of electrons. Now the bond pair of electrons which is present between this carbon and hydrogen will distribute between these two carbon atom, and this pi electrons will shift on to oxygen once again. So when these bond pair of electrons are shifting over here, there develops a pi bond over here, but this hydrogen will become free. But since we are having a lone pair of electrons on the carbon atom, this will donate it to the hydrogen atom so as to make a bond between carbon and hydrogen, so that we will be getting the compound like this. So here there is a double bond, here also double bond, and this O minus, and here there develops a double bond C, H, Cl and one more Cl. So two Cls are there, and now this resulting compound will once again reacts with the base OH minus. So this OH minus will be donated to the carbon atom, and in order to balance the valency, the chlorine atom will get eliminated in the form of Cl minus, and that Cl minus will combine with the K plus part of this KOH material. So this Cl will come out in the form of Cl minus. So that we will be getting the compound like this one. So here we have the double bonds, and here we are having O minus, and here C, Cl, single bond, OH, and here also we are having H. And now this electron density, the negative charge which is present on the oxygen atom, will be donated to the hydrogen, and this bond pair of electron which is present between the oxygen and hydrogen will shift over here, so that to balance the valency, the Cl will once again eliminates as a Cl minus. So here one more Cl will get eliminate, and finally we are going to get OH, and here C double bond O remaining with H. That is the final product of our interest, that is salicylaldehyde. This is the detailed mechanistic pathway for the conversion of phenol into salicylaldehyde, and this mechanistic pathway is having great importance in understanding the path by which the phenol can be easily converted into salicylaldehyde.